Why do we need this heat capacity? The typical question is, compute how much energy you need to heat one kilogram of water from 20 degrees Celsius to 80 degrees Celsius. You start with the definition. This one doesn't tell you how you are heating. You are heating at the constant volume or you are heating at the constant pressure. So you have to guess. So you are guessing that the most natural process would be you have a pot open, you put the heater down and you heat. So it's a constant pressure. So you know there would be delta H of delta T and you know at constant pressure these two are equal, so you find that this is Cp times delta T. Again, this is not perfectly right. The perfectly right definition should go like that. Cp is dH over dt, and the heat is the integral from temperature 1 to temperature 2 over dH dt times dt, so integral over t1 over t2 Cp times d, of course this is capital T. This is the correct way of calculating these things. Now, if you assume that Cp doesn't depend on temperature, and now we are from 20 to 80, probably doesn't depend very much, this is almost equal to, if you take the Cp out, T1 to T2 dt, and that is of course equal to Cp of T2 minus T1, which is equal to Cp delta T, which you get here. But now, again, this is the almost equal sign. It means that that formula is assuming that the heat capacity doesn't depend on temperature. You have to be careful with this. Sometimes it may depend on temperature. So why this is important? Because you are very often asking a chemical question. We want to heat something from one temperature to another. How much energy you need for this? So there is no chemical reaction happening, just physical process. So the heat capacity gives you the possibility of calculating the required energy for physical processes of heating. Good. Let's finish this one. Now, we should also discuss the following thing. H2O, in fact, can be considered in three different H2Os. This is very important for thermochemistry. You have always to write here in which state it is. It is gas, it is liquid, or it is solid. So gas, liquid, solid. Turns out that the heat capacity at, I guess, constant pressure for the gas, it's 34. Cp for the liquid, 75. And Cp for the solid is 37. So you see that the same substance, but this may be changing very strangely depending on the state the solid is, what the substance is. Good. Next thing is we should be able to predict heat capacity for of gases. Why? You should think what the heat capacity is, what the internal energy really is. So if you are giving energy to your system, the energy can be taken in a kinetic energy or a potential energy. So when you are heating, the system can be traveling much faster, or maybe the distance between two different atoms will be growing a bit farther. So for example, when the system is cool, the distance is here, but when the system is hot, the atomic distance is growing a bit. In fact, both of them happen. Both potential energy and kinetic energy is altered, but the first one is the kinetic energy. Kinetic energy requires, I will show you in a moment what it really means. So when you think about the heat capacity of gases, so how much heat you are adding to the substance, to the chemical, to the molecule, and what is happening inside, first we have to consider the internal energy. And the internal energy can be transferred into three different energies. Translational energy, rotational energy, next one, vibrational energy, and finally, electronic energy. Now to activate translational energy, you just need to be above 0 Kelvin. To activate rotational energy, you probably need just temperatures higher than, let's put 100 K. To activate really vibrational energies, you need probably temperatures higher than 1000 K. And to activate electronic energy, you need temperatures higher, let's say then 3000 K. Good. So now we can understand maybe more or less what is happening. When you give energy to your molecules, and the temperature is very low, let's say 20 Kelvin, and it's gas, everything will go to the translations of the molecules. The molecules will be traveling on the straight lines on the x-axis, y-axis, and the z-axis. Now, when the temperature is around 100 Kelvin or higher, they will be not only traveling on straight line, but they also will be rotating in 3 different possible directions. But when the temperature is really higher, then we'll be not only rotating, but also vibrating in all possible directions. And when the temperature is really high, but this is a bit difficult because 3000 Kelvin, it's pretty high temperature. Most of the chemicals are not stable to survive this temperature. So not many molecules can absorb electronic energy in the form of just heat. But now we are trying to understand what happens, how the heat energy is entering the molecules inside. Good. We said that for translational energy, there are 3 independent directions. X, Y, and Z. This is simple. I call it translational energy on X, translational energy on Y, and translational energy of Z. Now I put equal sign between them. Why? Usually in science, except for relativistic science, you assume that the space is isotropic. It means wherever you look, the equation should be the same. And here it's exactly similar story. The translation here, here, here should be the same. You see that gravitation here shouldn't really matter for the molecules. So we know that the energy growing for this one, like that, it's exactly the same in all possible directions. It turns out that you also can relate it to the temperature. Okay, I changed T for kinetic energy. Kinetic energy. Kinetic energy. And this is equal this. You can connect it with temperature. It turns out that it's very easy to connect the kinetic energy of traveling on the lines with the temperature in the system. Maybe I should be here more careful. Instead of putting R, I put here K. K is a Boltzmann constant. And you know that R is just the number of molecules in 1 mole time K. So this one is for a single molecule. What I wrote before here with R was for 1 mole of molecules. Good. Let's analyze similar way the rotational energy. How many independent directions? 2? 5? Oh, okay. Looks like we have nice situation. 5, 2. How many different independent directions for rotational? 3, 2, 3. This is 2. You already said, right? 6. 2. You said already? Okay. I come to it later.
2.
2 and 2, right? Okay. What are all possible answers?
2 or 3.
And this is the correct answer, 2 or 3, depending what is the shape of the molecule. Imagine the molecule like that. This molecule can be rotating in this direction. This molecule can be rotating in this direction or rotating in this direction. 3 independent rotations. But when you have only 2 atoms, for example, or a linear molecule in general, this molecule can be rotating like that, can be rotating like that. But when the molecule is rotating like that, you don't see it. So there is no rotation in this case. So the answer is 2 or 3. 2 independent. Okay. Too lazy to write it. Directions, and here is 4 linear molecules. And 3 independent directions for other molecules. And again, for each independent direction, we get the energy contribution per molecule, 1/2 kT. Good. What about vibrations? How many vibrations per molecule? How many independent directions for vibrations for molecule? Bonds. How many bonds? How many bonds? How many bonds? Imagine this molecule, benzene, another benzene. The separation is around 3 angstrom. This is too much for a bond. But the energy of this bond is around 10 kcal per mole. So it's a chemical bond. It's a weak chemical bond. Now, these two can be vibrating like that or not. Imagine if there is no minimum, right, they would clap to each other. In the other direction, they would go to infinity. So there must be some minimum in the energy between them. If there is a minimum, there must be some vibration levels on the minimum. So there is no bond, but there is. So the number of bonds is not a good quantitative measure of calculating the number of vibrations. Some other proposals? No, this is difficult. I'm not expecting you to know, but maybe. Well, it turns out that every atom can go X, Y, and Z. If you have 5 atoms, they can go to 15 different directions. But when all atoms go to X, you have just the translation on X of all the molecule, or translation on Y, or translation on Z. So out of 15 possible modes, 3 of them goes to translations. Similar, if all the atoms are moving that way that the molecule is rotating, you have 2 or 3 rotations out of these 15. So the final number of vibrations is 3n minus 5 or 6, depending if it's linear or not linear molecules. When n is a number of atoms. So saying once again, number of vibration is 3n minus 5 independent directions for linear molecules or 3n minus 6 independent directions for nonlinear molecules. And of course, for each independent direction, you have 1/2 kT. But the the thermodynamics we are discussing is the thermodynamics at the room temperature. So in fact, you see that only these two types of internal movements are contributing here. So we have that for the linear molecules, the internal energy, change in internal energy, can be related like 3/2 RT kT plus 2/2 kT, which is totally 5/2 kT. And for nonlinear molecules, the change in the internal energy caused by the temperature will be equal to 3/2 kT plus 3/2 kT, which totally gives 6/2 kT, or if somebody prefers, just 3 kT. This is per molecule. When you consider what would be the change of the molar energy, then it would be either 5/2 RT or 3 RT. Linear, not linear. Of course, and I'm forgetting everywhere to write, if this is a change of energy, there should be a change of temperature. Change of temperature, change of temperature, change of temperature, change of temperature, change of temperature. So now what we are getting is that the heat capacity at the constant volume is the, as we said, and plugging what we get there, 5/2 R, of course this is molar, R for linear molecules, and 3R for the nonlinear molecules. What is the heat capacity at constant pressure? Molar one, of course. We said is delta U delta H, of course. Which is delta U plus delta PV over delta T. And now I can rewrite this one a bit. For the ideal gas, and we have here gases, so this would be almost equal at the normal temperatures. Instead of writing PV, I can write here nRT. And look here, I have molar one, so for 1 mole, so N is equal to 1. And R is a constant. So what I'm getting is delta U over delta T plus R delta T over delta T, which is equal delta U over delta T plus R, which is of course equal to 7 over 2R for the linear molecules and which is equal to 4R for nonlinear molecules. Good. Why this is important? Very often they ask you how much energy you need to heat gas from one temperature to another temperature, and then they don't give you any data. Then you know that if they don't give you any data, you can make an approximation that this is ideal gas and use the ideal gas specific heat at the constant pressure or constant volume. Good. Let's go further. Let's start doing changes. We already know that if you are just doing the changes in the temperature, we already know how to calculate the heat required for such changes. Generally, everything what the thermochemistry wants to do is to calculate how much energy you need for processes. These are just heating processes, and we already know how to deal with this. Now we are doing some physical processes like vaporization or heat required for physical processes. We know that the heat would be equal to the change of the enthalpy, and change of the enthalpy, it means that there will be the enthalpy of molecule after process minus the enthalpy of the molecules before process. Then it's easy. Then we have the energy or the heat required for vaporization. It's called enthalpy of vaporization. Notice that it doesn't make sense to speak about vaporization at constant volume. No, maybe it makes sense. Okay, skip this. So we have at constant pressure the vaporization. There would be the enthalpy of liquid, enthalpy of gas, minus the enthalpy of liquid. But now you may ask me, but where do we take this from? That's a different story. Your book at the end has more than 20 pages saying experimental data. And this experimental data you have different data. You have like molar mass, enthalpy of formation, free energy of formation, molar heat capacity, and molar entropy. As so far, out of these 5 different things, we know what the molar mass is, and we know what the molar heat capacity is. Now we should understand what are the next one. What is the enthalpy of formation? To understand, we should understand what is pure element. So the pure elements for hydrogen, it would be H2. For oxygen, that would be O2. For carbon, of course, gas. For carbon, it would be graphite, which is most often written as CGR. And now what it means? Pure element, or element in the pure form, is the most stable form of any element at given temperature. So for oxygen, you can possibly write atomic oxygen, but atomic oxygen are not stable. They want to connect to another oxygen and make a molecule. So this is the most stable form of each element at given temperature. For carbon, it is a graphite. And these tables, experimental data, it is given in Appendix 2, they always give you the most stable form of every element. Now, the important thing is, by definition, enthalpy of formation of pure elements in their standard form is 0. Nice. So now you can take the most stable form of hydrogen, which would be the gas hydrogen, and you can react with the most stable form of the oxygen, which is the gas oxygen, and you know that you need just 1/2 here, and you will create H2O. And by measuring experimentally how much energy is produced by this reaction, you find what is the enthalpy of formation of water. But there is a danger here. The danger here is that I didn't say if this is gas, this is liquid, or maybe possibly it's solid. if you think about that, H2 plus O2 is explosion. It gives a lot of energy. So the only possibility is if it's gas or liquid. Probably it will never give solid after the explosion. But formation of gas water, it has different energy than formation of liquid water and has different energy than formation of the solid water. If you want to calculate them, you just have to include the enthalpy of vaporization here and enthalpy of fusion here. Well, so coming back to our physical processes, if you want to calculate the enthalpy of vaporization, you have to check what is the formation of your gases, the enthalpy of formation of your gases, what is the enthalpy of formation of your liquids, and just subtract these two numbers. Similarly, if you want to calculate the heat needed for fusion, then you just check the difference in enthalpies for fusion. So there would be solid minus liquid. What time is it? 12? And of course, you can also consider the opposite process here. Namely, how much heat will be produced or required for liquefaction. So no vaporization, but the opposite process. And what it is, of course, there will be the enthalpy of liquefaction. And of course, there would be the enthalpy of the liquid minus the enthalpy of the gas. And you see from this one that is exactly opposite than the enthalpy of vaporization. Okay, that's very nice. Because I can use it with the different sign, different process going the right direction or left direction. Okay, next class we just do the same for chemical reactions. We start using this for some 1 or 2 examples, and we start talking about entropy. Thank you very much for today.